Do I have some head nods? All right, good. Got the document. Let's look at the coordinate system. When we started back, way back when, and we talked about two coordinate systems that we were going to use. And this is our y, and this is our x, and this is our normal, our orthogonal coordinate systems that we've had. And then we also talked about that we could use a polar coordinate system, where we looked at this being r, the radius of our circle, and this being our angle theta, and that we could describe this as r theta. So now if I'm traveling around in a circle, and I'm actually using motion in a circle, there's my center, and I start from here, and I go around this circle here, this we can talk about as being an S. All right? We can look at that as being an S. This is still R, this is still R, and this is my angle between. And if I want to look at that, we can define this angle as being S divided by R. Particularly when we're talking about being very, very small angles. Okay, we're talking about being very, very small angles. If I look at my triangle like this, we'll do it that way. There's my angle. This is R. This right here is the distance that we're talking about, and that's S. And as long as my angle is small, that works. And you can actually go in, and if we know that this is the opposite, right? This is R and this is R as well, if I'm doing it really, really small. But if I did my opposite over the hypotenuse, if you find the sine of the angle is approximately equal to the angle, provided that my angle is less than 10 degrees. And you can actually go in and look at that and play with it in your calculator and show that that's actually the case. So if we look at this and look at our very small movement, our angle is really, really close to the linear distance. So I can actually go back and forth between my theta and my distance, and I can have r theta is equal to my distance, and I can actually have that piece, and I can look at that as displacement. Okay? I can look at that totally as displacement, which gets us to, because we know that on a linear system, that velocity is equal to my change in position with respect to a change in time. And if I'm looking at what we talked about in one of the videos, my angular velocity, and this will be angular velocity, is going to equal my change in my little displacement divided by my change in time. Okay? So we've got that not displacement, this is change in my angle divided by my change in time. I'm getting ahead of myself. So my change in angle divided by my change in time is going to be my angular velocity. Let's look at the units, because this is where things get funky for circular motion. So this is going to be in meters per second, and this over here, we don't do it in degrees. We're actually going to use radians. Radians are going to be our angle, and this is radians per second. Now, a lot of times we're not going to use the term radians, so we'll see it like this, but most of the time we'll ditch the radians and we'll have an angular velocity in 1/seconds. And if I have something in 1/seconds, if you remember it from chemistry class, that's a frequency. So we'll see this again and again, because we'll end up relating this later on to looking around. If I have an object that's traveling around in a fixed circle, it's going to continue to go back and forth and around in a fixed circle, and I can look at number of cycles per second, or what we saw when in the Hewitt-Druitt video, he talked about RPM, and that is revolutions per minute. So the number of times that I go around, I can actually convert that into an angular velocity. So I can give you an angular velocity a number of ways. I can tell you how many times it went around the circle. I can tell you, how many times it goes back and forth. We can do revolutions per minute, and I can come back and get an angular velocity. So let's do one real quick. So let's look at, we want to find the linear distance traveled and I'm going to look at, we're going to make this a tire, and we're going to use a P on the tire. Okay? So all of us usually have tires that are labeled something, so I'm going to use Pirelli tires. And we're going to look at the capital P on a Pirelli tire. And we're going to say that this Pirelli tire travels 2.5 times around 2.5 times around the circle. Okay? We want to know the linear distance traveled. And we're going to use that this tire is, I'm going to use that that's 10 inches. So it's going to be an interesting tire, but we use as 10 inches. So if it's 10 inches, it's going to be 25.4 centimeters in radius, which means it's going to be 0.254 meters is my radius. The circumference of my circle, if you don't remember the circumference is 2 pi r. So if something travels 2.5 times around, it's going to be 2.5 times the circumference, which will be 2.5 times 2 pi r, is going to be how far the linear distance that were to travel. So if you think about it as being the toilet paper on a toilet paper tube, if I take my toilet paper and unroll it 2.5 times, how much toilet paper have I got extended out on the flat surface? That's exactly what we're doing here when we're looking at this going around. And if I do that, that's going to give me 5 pi r. And that will give me 5 pi times 0.254 meters. Let's see if I brought my calculator. Yes, I did. Woohoo! Huh. And funny, there was a calculator on the counter here. Okay, so if I do 5 times pi times 0.254, it would say that that linear distance that the letter P moved around was 3.989 meters, or about 4 meters, as it went around the circle. So you're going to have to start thinking in a little different dimensions that we have. One of the other things that we're saying that this is in radians. So what you're also going to have to do is make sure your calculator is in the right units when you're working your problems. So right now mine is in degree. How I change it on my calculator is I can go to a screen that looks like this, and I get degrees, radians, and gradians. You're going to want to be in radians when you work these problems. And radians are related to what's the angle in my circle. So if I look at my circle, and we look at how we measure angles. So if I start from this spot here, this would be 180 degrees, right? The top up there, that would be 180 degrees. That is pi radians. 360 degrees is equal to 2 pi radians. So you're going to be able to convert back and forth between degrees and radians, but I'm going to be working with my unit of pi in order to get there. So we'll be dealing with those lovely pieces. If if I tell you, let's think of the penny example that he had on the record. So we had our penny here, and we want to know the angular frequency or the angular velocity of this penny. And he gave us that the record was traveling in 33.3 revolutions per minute. Okay, in revolutions per minute. So we know we can, so if I want to do this and find it in terms of seconds, we're going to go 33.3 revolutions per minute. And I have 1 minute is 60 seconds. And I'm going to end up in revolutions per second. 33.3 divided by 60. I'm going to get 0.555 revolutions per second. And 1 revolution is equal to 2 pi radians. And so I can look at that, my revolutions per second, it could be number of cycles per second, is going to be my angular velocity. So some things to kind of think about as we go through it. So now what we've got so far is we've got velocity, this is linear, is my change in position versus my change in time. I've got over here, I have that my angle is equal to S divided by R. I'm going to make it cleaner. S divided by R is my angle. So my S, if I want to convert to a linear distance, it's going to be R times my angle. Now I've got my angular velocity is the change in angle with respect to time. Now if I go ahead and put in my angle here, I'm going to get the change in S divided by R with respect to time. That's going to give me 1 over R times velocity, and I get R omega is equal to my velocity for my linear velocity. Which is exactly what we saw in the Hewitt-Druitt video, where they were talking about which horse on the carousel goes around faster. So I can go back and forth, so I can convert back and forth between my linear coordinate system and my rotational coordinate system. So one more step further. So we know that acceleration in the linear sense is my change in velocity with respect to a change in time. So if I'm looking at, and we're going to use the Greek symbol alpha, is equal to the change in angular velocity with respect to time. That is going to be my definition there. We can also convert back to this one if I look at my, I don't know how to do this. Okay. That if I do this is change in omega over R. No. Omega is V over R. All right, with respect to time, change in time. So I get a change in velocity with respect to a change in time, 1 over R. So R alpha is going to equal acceleration. So we can convert back and forth for that one as well. So what this gets us, and this is where we're going to stop, but what this gets us is we're going to end up with the same types of equations that we've had before. So I have velocity is equal to velocity initial plus acceleration times time. I've got a change in position is equal to my initial velocity times time plus 1/2 AT squared. I have V squared is equal to V initial squared plus 2A change in position. I'll end up with omega initial plus my angular acceleration times time. My change in angle is equal to my initial times time plus 1/2 A, and this is alpha T squared. And I get omega squared is equal to omega I squared plus 2 alpha change in angle. And in you guys' book, this is around 7.7, 7.8, and 7.9 for your equations. That should get you started. We'll see you Wednesday.